theorem on the first chapter is what? Let fxy be continuous at point x naught y naught. Here is right continuous, not constant, continuous at point x naught y naught. Then prove that f x y naught is continuous function at x is equal to x naught. This is one variable function. And f x naught y is continuous at y equal to y naught. Right here, y equal to y naught. Y equal to y naught, which is y naught, where f x y naught and f x naught y being a function of one variable. This is the function of two variables. And what is given? The function f x y is continuous at x naught y naught. And what we have to show? We have to prove this f x y naught is continuous at x is equal to x naught, and it is f x naught y, f x naught y, don't write here 0, is continuous at y equal to y naught. So what is given? We write first meaning of the given. So as fxy is continuous at x naught y naught, so by using definition what we have, this is the limit. The function is continuous at x naught y naught means limit at x naught y naught of fxy is equal to f of x naught y naught. This limit exists and is equal to f of x naught y naught because of the continuous function. When the function fxy is continuous at this point x naught y naught means limit xy tends to x naught y naught of fxy is equal to f of x naught y naught. These two are same because the definition of continuous function, when the function is continuous, fxy is continuous at ab, if limit xy tends to ab, fxy is equal to f of ab. So instead of a and b, here is x naught and y naught. So the function is continuous at x naught y naught. So we have this, that limit at x naught y naught of function fxy and the value at x naught y naught both are same. This limit exists and is equal to f of x naught y naught. And the limit of this function is f of x naught y naught. Therefore, what we have, for every epsilon greater than 0, there exists delta greater than 0 such that mod fxy minus L is what? F of x naught y naught is less than epsilon whenever root x minus x naught square plus y minus y naught square is less than delta. So we write this statement that this is less than epsilon whenever this means what? This is less than epsilon if this is less than delta. That is, if this is less than delta, implies mod fxy minus this f of x naught y naught is less than epsilon. This is the definition of limit. That is the first definition. What is the definition of limit? We can write the equivalent statement of that. So what is the definition of limit? Limit is what? Limit of fxy is L. So this is the definition. When we say the limit of fxy as xy tends to ab is L, if mod fxy minus L, for every epsilon greater than 0, there is delta greater than 0, said that mod fxy minus L is less than epsilon whenever x minus a bracket square plus y minus b bracket square is less than delta. That is, this is less than epsilon whenever this means if this is less than delta, this is less than delta, then mod fxy minus L is less than epsilon. So we can write this statement as this is less than delta implies this is less than epsilon. So in this our theorem, this AB are x naught y naught and L is f of x naught y naught. So right here f of x naught y naught, and right here A and B as x naught y naught. So that is our theorem. So this is by using the definition of limit of two variable functions, simultaneous definition of simultaneous limit. So this is given that the function fxy is what? The function fxy is continuous at x naught y naught. So this is important theorem as far as the exam concerned. So we have this that root x minus x naught square plus y minus y naught square is less than delta implies mod fxy minus f of x naught y naught, that is the answer here, is less than epsilon. This is suppose star equation star. So this is given. And now what we have to show? We have to show the fxy naught is continuous at x is equal to x naught. So when this function fxy is continuous at x is equal to x naught, if for every epsilon greater than 0, there exists delta greater than 0 such that root x minus x naught square plus y naught minus y naught square. That is only we have root x minus x naught square. Y naught minus y naught is 0. X minus x naught square, root of x minus x naught square means x minus x naught, just x minus x naught. Take positive root, that is mod x minus x naught is less than delta, implies mod f x y naught, because the function is f x y naught instead of f of x x y, minus f of x naught y naught is less than epsilon. Okay, so what we have to show? We have to show this. In order to show fx y naught is continuous at x is equal to x naught, what we have to show? For every epsilon greater than 0, because of the definition, when the function fxy is continuous at x naught y naught, if this happens. So when the function fxy naught is continuous at x is equal to x naught, so here fxy is fxy naught. So write here fxy as f of xy naught, and write y as y naught, y as a y naught. So if you write y as a y naught, then this is 0. That is what we have to show. X minus x naught is less than delta, or mod x minus x naught is less than delta, implies mod f x y naught minus f x naught y naught is less than epsilon. So mod, consider, we start with mod x minus, so mod x minus x naught is less than delta. We start with this. Mod x minus x naught is less than delta, and we have to show mod f x y naught minus f of x naught y naught is less than epsilon. So start with mod x minus x naught less than delta, implies, so we adjust, that's y minus y naught minus y naught square. Here just write y naught, x minus x naught square, root x minus x naught square, plus y naught minus y naught. Y naught minus y naught is 0, so add just 0. So we write x minus x naught as root x minus x naught square, plus right here y naught, here write y naught minus y naught square is less than delta. Both are same, because if we find x minus root x minus x naught square plus y naught minus y naught square, then it is 0. Then it is, we have the answer x minus x naught. So just write y naught minus y naught square, add the 0, and that is add 0. And this implies, by using this, if this, then we have this by using star. So here is x minus x naught square, here is y naught minus y naught, just write y naught, y as y naught. So here we write also y as y naught. So what this implies, f of x y naught minus f of x naught y naught is less than epsilon by star. If we have this, then we have this by using star. So if we have this, therefore we have this. Here write y naught. If we find x minus root x minus x naught square plus y minus y naught minus y naught square, we have the answer x minus x naught. So this is the another form of x minus x naught. And this implies, by using this, we have this. That is replace y, because here is y naught minus y naught. So replace y by y naught. So f of mod f of x y naught minus f of x naught y naught is less than epsilon. We have this, and this means we start with this, and we have this means limit x tends to x naught, f of x y naught is f of x naught y naught. That is, this limit of the function f of x y naught is exists at x is equal to x naught and is equal to the value at x naught y naught at x naught. That is, we have this limit x tends to x naught, f of x y naught is equal to f of x naught y naught. And this means f of x y naught is continuous at x is equal to x naught. Similarly, the proof that we have to show f of x naught y is continuous at y is equal to y naught. So start with mod y minus y naught is less than delta, and write mod y minus y naught as root x naught minus x naught square. That is just add 0. X naught, here write x naught minus x naught square plus y minus y naught square is less than delta. So repetition of this. And this implies y star. If this is less than delta, then we have this. So here is x, here is x naught. So just write here x as x naught. So what we have, mod x naught my y minus f of x naught y naught is less than epsilon. And this means limit y tends to y naught f of x naught y is f of x naught y. And therefore f of x naught y is continuous at y equal to y naught, and hence theorem. So this is important theorem. Define simultaneous limit. That is the previous definition. Limit x y tends to ab of f x y. So then the next problem is if the repeated limits exist and are not equal, then simultaneous limit does not exist. This is the only relation between repeated limits and simultaneous. Otherwise, there is no relation between repeated limits and simultaneous limits. So example is find repeated limits and simultaneous limit of this function. So first repeated limit, limit x tends to 0, limit y tends to 0, f x y. So if f of x y is this, x minus y divided by x plus y. So first find limit as y tends to 0. So then substitute y. So what we have, x by x, and that is 1, and limit of 1 is 1. So we have 1. So don't write this. Only write x by x, that is 1, and limit of x 1 as x tends to 0 is 1. Then limit y tends to 0, x tends to 0, f x y. Another repeated limit. Y tends to, just find limit of first x tends to 0. So if we substitute x is equal to 0, then we have minus y by y, and that is minus y by y is minus 1, and limit of minus 1 is minus 1. And therefore these repeated limits are not equal, and therefore simultaneous limit does not exist. Actually, we can check directly, write that simultaneous limit of f x y as x y tends to 0, 0 does not exist. Or we can solve separately that simultaneous limit does not exist. How we can solve the simultaneous limit does not exist? We will find the limit along path y is equal to mx. So limit x y tends to 0, 0 f x y along path y is equal to mx, limit x tends to 0, f of, right here, f of x mx. And f of x mx is what? This is f of x y. So write y as mx. So x minus mx divided by x plus mx. Take x as common and cancel. 1 minus m divided by 1 plus m. Limit of this factor with respect to x tends to 0. So which is depends on m, and therefore limit along different path is different, and therefore limit is simultaneous limit as x y tends to 0, 0 of x y does not exist. So we can directly claim that the repeated limits are not equal, and therefore simultaneous limit does not exist. But it does not mean that if the repeated limits exist and are equal, then simultaneous limit exists. There is no relation between the existence of repeated limit and equality of repeated limits. Then simultaneous limit exists. So some more examples on the chapter. So this is the second chapter actually, these are some examples, more examples on the first chapter. Define simultaneous limit of function. That is the definition given at the start of the chapter. Simultaneous limit definition. And find limit of the function fxy as a function cos x cube minus y cube divided by x square plus y square. If there is a x square plus y square term, then use the polar coordinate as xy tends to 0, 0. So this is the function fxy as cos x cube minus y cube divided by x square plus y square, and we have to find the limit xy tends to 0, 0 fxy. So limit xy tends to 0, 0 cos x cube minus y cube divided by x square plus y square. Substitute x as r cos theta, y as r sin theta. Therefore x square plus y square is r square. And as xy tends to 0, 0, r tends to 0. Because what is r? R is x square plus y square. If x is 0, y is 0, then r is also 0. Okay? Because r square is what? R is what? Root x square plus y square. That is root 0 plus 0 is 0. So as xy tends to 0, 0, r tends to 0. So is equal to, continue the problem, that is equal to limit xy tends to 0, 0 replaced by r tends to 0 cos x cube means r cube cos cube theta minus r cube sin cube theta by r square. Take r cube as common, then r square get cancelled with value of x square plus y square as r square. Then we have r cos cube theta minus sin cube theta. And if we substitute r as 0, then what we have? Cos value of this quantity is it, suppose the cos cube theta is so if you substitute r as 0, then we have cos 0. 0 into this quantity is cos 0, and cos 0 is 1. So this is the answer of this problem. Limit x y tends to 0, 0, cos x cube minus y cube divided by x square plus y. So if fxy and gxy are continuous, right? Writing here the word continuous, not constant, continuous at AB, then fxy by gxy is continuous here, right? Continuous at AB if g of AB is not equal to 0. So when the function division of two function is continuous, if the denominator is not equal to 0, only this, that if g of AB is not equal to 0, that is the denominator is not equal to 0 at that point. And polynomial functions are continuous everywhere. If there is polynomial function, then it's continuous everywhere. So determine the set of points at which the function, this function, are continuous. Okay, so the answer of first function. So when the denominator is not equal to 0, actually x square plus y is polynomial function, so it's continuous everywhere. X cube minus 3x plus 2 is polynomial function, so by using this note, is continuous everywhere. But when their division is continuous, if the denominator is not equal to 0 at that point, so when the denominator is 0, x square minus 3x plus 2, what are the factors? X minus 2, x minus 1. So when this x square minus 3x plus 2 is 0, if x is either 2 or 1, and therefore this function fxy as x square plus y square divided by x square minus 3x plus 2 is continuous at every point except at x is equal to 1 and 2. X is equal to 1 and 2. That is, at 1 and 2, the denominator is 0. So at x is equal to 1, this is discontinuous. At x is equal to 2, this is discontinuous. So it's continuous at every point except at x is equal to 1 and 2. Or we can write fxy is continuous on set xy belongs to r square, such that x is not equal to 1 and x is not equal to 2. So again, the function f sin 1 by x into y is continuous for all points except x into y. X into y is 0. Except when this x into y is 0, at that point the function is not continuous. So fxy is continuous on the set xy belongs to r square, so that xy is not equal to 0. Where it is continuous except x is, so here is where it is continuous if x is not equal to 1 and x is not equal to 2. So right here, except means if the x is 1, then function is discontinuous. So when x is not equal to 1, then function is continuous. Like that. If x into y is 0, then function is discontinuous. So where the function is continuous on every point xy belongs to r square, where x into y is not equal to 0. Then the third problem is what? F of x, y, z is equal to 1 by y mod y plus mod z. Again, this function is continuous every point except where the denominator is not equal to 0. Okay, except where the denominator is equal to 0. Other than the point where denominator is 0. Except mod y plus mod z is equal to 0, and means mod y is equal to mod z minus mod z, right? Minus mod z of mod y is equal to minus mod z, and that is y is plus minus z, because mod y is what? Plus minus y. So the function fxy is continuous on the set mod y is equal to mod z, or mod y is equal to minus mod z, or write mod y plus mod z is equal to 0. So that the function fxyz is x plus y minus z is continuous at every point of R3. And this is the polynomial function, and so is continuous in R3. This is the polynomial function, and therefore is continuous everywhere in R3. So just write this sentence or write this proof that find the limit along that ABC be any point, and then we have to prove the function is continuous everywhere. So take any point from R3. And this function is continuous at ABC if this limit at ABC exists and is equal to f of ABC. So we'll find the limit x, y, z tends to ABC of f x, y, z. This is the definition of continuous function. So limit x, y tends to ABC, x, y, z tends to ABC of f x, y is what? X plus y minus z. And if we substitute x as a, y as b, and z as c, we have this answer. And what is f of ABC? It is x a plus b minus z. So both are same. Limit at ABC and the value at ABC both are same, and therefore f x, y, z is continuous at ABC. Right? Either this proof or this proof that the function, polynomial function is continuous everywhere, so this function is continuous everywhere. So these are some problems on the continuous functions, some different types of problems. Otherwise, the first type problems are, there are two types, we covered two types of problems, that is limit does exist and limit does not exist. Okay, so in the next lecture, we will start the next chapter, partial derivative. And I will share the homework problems on the chapter first uh, through our WhatsApp group. So solve all the exercise, and if you have any problem while solving exercise, contact me through WhatsApp.